Hello everyone, this is Shankar. In this video, I would like to discuss power electronics questions given in the recent GATE 2024 exam. Now, let us move directly into the video. The first question, of course, order of the questions will vary from the paper to paper. Now, here in this video, the first question is a forced commutated thyristor step down chopper is shown in the figure. Neglect the on-state voltage drop across the power devices. Assume that the capacitor is initially charged to 50 volt, that is nothing but source voltage, with the polarity shown in the figure. The load current can be assumed to be constant, that is at 10 ampere. Initially THM, that is nothing but main thyristor, is on, and THA, that is nothing but auxiliary thyristor, is off. Now we need to find out what is the turn off time available for the main thyristor in microseconds when auxiliary thyristor is triggered. So this question is basically from commutation circuits. In my lecture, I used to discuss this commutation topic in the chapter 3. Total power electronics was divided into 6 chapters. Out of that, this topic is from 3rd chapter, DC to DC converters along with the commutation techniques. Now, by seeing this circuit, say for example, whenever this auxiliary thyristor is turned on, you can say that the current direction, it will be like this, right? Therefore, in this process, constant current is flowing through capacitor. Then what happens? Capacitor voltage will try to charge from source voltage. Initial value is given as a source voltage, therefore you can also say that it is a minus VDC to plus VDC. So when constant current is flowing through capacitor, what happens to voltage across the capacitor? It will vary linearly with a slope of that current by capacitance value. Then whatever capacitor voltage is there, that will directly apply across the main thyristor. So just for our clarity, I can represent in this diagram. Now notice this diagram. Whenever auxiliary thyristor is turned on, constant load current is flowing in this direction. Therefore, capacitor voltage will charge from, now see here, minus VDC to plus VDC, right? So this capacitor voltage will directly apply between anode and cathode terminals of the main thyristor. Now we need to calculate what is the circuit turn off time. So if you recollect the definition for circuit turn off time, the time taken for the thyristor for which how much time the negative voltage is applied across the thyristor in such a way that the current comes to 0 and the device will get turn off. Now suppose if you take in this triangle PQR, you can define it like this. In triangle PQR, if you apply the slope concept, I naught by C is equal to PQ divided by QR. So in this, I naught divided by C is equal to PQ is source voltage. Ignore that minus symbol. We need to focus on the magnitude part, divided by circuit turn off time TC. Therefore, TC can be expressed as C multiplied with VDC divided by I naught. Now by substituting the data, capacitance value is given as 10 microfarad, source voltage is given as 50 volt, and the load current is given as 10 ampere. So 10 microfarad multiplied with 50 volt divided by 10 ampere. So 10 and 10 will cancel. We will be remaining with circuit turn off time of 50 microsecond. Okay, so this is the answer for the question. As the question is asked in circuit turn off time or the turn off time available for main thyristor in microseconds, the answer could be simply 50. So now let us move to the next question. This question is from basics of power semiconductor devices. Normally I used to explain this concept in the chapter 1. In the following devices having similar power ratings, which one of the following is fastest device? So whatever the condition is, among all the power semiconductor devices, the fastest device will be power MOSFET. Therefore, we need not to think about remaining options also. Power MOSFET will be the straight answer. Of course, this is given for 1 mark question. Previous question is also for 1 mark. Now, let us move to the next question. This is again for 1 mark. A single phase triac based AC voltage controller feeds a series RL load. The input AC supply is 230 volt 50 Hertz. The values of resistance and inductance are 10 ohm and 18.37 millihenry respectively. What is the minimum triggering angle of the triac to obtain controllable output voltage? Now, in case of AC voltage regulator, with RL load, control range for an output voltage, control range for V0 is alpha should be greater than or equal to phi, where phi is load power factor angle, and at the max you can increase up to 180 degree. Therefore, let us calculate what is phi here. Phi is equal to load power factor angle. You can write it as tan inverse omega L divided by R. What is omega here? 2 pi f. So tan inverse 2 pi f L divided by R. Now let us substitute the data. 2 pi into frequency is 50 Hertz, inductance is 18.37 into 10 power minus 3 because it is given millihenry divided by 10 ohm. So if you calculate this value, it will come around 29.99. I can round it off to 30 degree. Therefore, minimum firing angle or triggering angle should be 30 degree. Minimum firing angle should be 30 degree. So option D will be correct answer for this question. Now let us look into the next problem. A single phase full bridge voltage source inverter. This question is from inverters chapter. Feeds a purely inductive load. The inverter output voltage is a square wave in 180 degree conduction mode. The fundamental frequency of the output voltage is 50 Hertz, because as f is equal to 50 Hertz, you can also say that one cycle time will be 1 by f. This is equal to 20 milliseconds. Just for calculation, keep it that. If the DC input voltage to the inverter is 100 volt and the value of load inductance is 20 millihenry, what is the peak to peak load current in ampere? Now, two things you need to understand here. Given circuit is voltage source inverter and the given load is purely inductive load. So with this combination, you can draw output current and you will get that output current is a triangular wave. So for a quick reference, I just plotted here. Now this is a output current waveform, that is current flowing through pure inductive load in voltage source inverter. Now as the time is measured plotted in x-axis, that is the millisecond scale, one cycle time will be 20 milliseconds. So one cycle will complete by this time. So that is a 20 millisecond. So just as per the symmetry, this interval will be 5 millisecond and this is another 5 millisecond. Cumulatively it is 10. Like that, finally it will reach us to 20 millisecond. Now in this triangle PQR, just like previous question, if you apply slope concept VDC by L, so what you will have here in triangle PQR, the slope is VDC by L is equal to QR divided by PR. So here source voltage is given 100 volt divided by load inductance is 20 millihenry is equal to QR. This is a peak current of the output divided by PR. This is a 5 millisecond. This is a 5 millisecond. Therefore, QR will be, I can cancel this 10 power minus 3 on both sides. Therefore, QR will be 25 ampere. Now, we need peak to peak value of output current. So, what is that? See, this is one peak and as per the symmetry, this is another peak. Then it will be 2 times QR. So that you will get 50 ampere. So, answer for this question will be 50. This is a inverters question from GATE 2024 exam. Now, let us move to the next question. Let us read the question first. In the DC to DC converter shown in the figure, by seeing the circuit diagram, you can easily understand the circuit given here is boost converter. So, in the DC to DC converter or the boost converter circuit, the current through the inductor is continuous. The switching frequency is 500 Hertz. The voltage V0 across the load is assumed to be constant and ripple free. So, you have to calculate peak inductor current in ampere. So, let us do some step by step. What is given here? V0 is given 40 volt which is constant and source voltage, let me call it VDC, this is a 20 volt. Therefore, for the boost converter, the equation will be under continuous conduction VDC divided by 1 minus D. By substituting these numbers, you will get duty cycle ratio of 1 by 2 or 0.5. Because input voltage 20 and output voltage is double, therefore duty cycle ratio will be obviously 50% in case of boost converter. Next, let us also calculate quickly what is I0. I0 is output current V0 by R. V0 is given as 40 volt, load resistance is given as 10 ohm, hence it will be 4 ampere. Now, let us also find what is the average value of inductor current. In case of boost converter, average value of inductor current, we can also say that input current, that will be I0 upon 1 minus D. 4 divided by 1 minus 1 by 2, it will give you 8 ampere. So, average value of inductor current will be 8 ampere, but we want peak value of inductor current. So, if you look into inductor current waveform, it will be something like this. It is a triangular waveform. This is a inductor current. Okay. So, average value of this waveform will be this yellow line. Let us say this is IL. Okay. And this particular now say for example, this one is peak to peak ripple delta IL. Therefore, the peak value in inductor current can be expressed as average value plus half of peak to peak ripple, delta IL. Now let us calculate what is delta IL. Expression for delta IL in boost converter is VDC by L multiplied with D into T. Source voltage is given 20 and inductance value is given 2 millihenry, 2 into 10 power minus 3. Duty cycle ratio is 1 by 2. Cycle time will be 1 by 500 hertz. 1 by 500 hertz. So by simplification, you will get this value as this 2 cancel here. This particular value 10 power minus 3 and 1000, it will cancel. Therefore, this will be around, let me calculate, 20 divided by 2 millihenry into 2 into 500, it will give you 10 ampere. Okay, so this is a 10 ampere. Delta IL is a 10 ampere. So peak value of the inductor current, how much you will get? 8 plus 10 by 2, it will give you 13 ampere, 13. So answer for this question will be 13, 13, right? Now let us move to the next question. Now this question is basically application of phase controlled rectifiers in the drives. Even though drives is officially not in the GATE syllabus, but still we can consider this is an application of phase controlled rectifiers to control the speed of a DC motor. Okay. Now let us see the question here. A single phase fully controlled thyristor converter bridge is used for regenerative braking of a separately excited DC motor with the following specifications. The rated armature voltage 210 volt and rated armature current of 10 ampere, rated speed of 1200 rpm, armature resistance of 1 ohm, input to the converter bridge 240 volt at 50 hertz. The armature of the DC motor is fed from the full controlled bridge and the field current is kept constant. Assume that the motor is running at 600 rpm and the armature terminals of the motor are suitably reversed for regenerative braking. If the armature current of the motor is to be maintained at the rated value, find the triggering angle of the converter bridge in degree. Okay. So what we will do at rated conditions, let us find out back EMF and let us call this is a EB1, that will be terminal voltage minus armature drop. Armature drop will be 10 ampere into 1 ohm. So 210 minus 10 will give you 200 volt. Okay, 210 minus 10 will give you 100 volt. Now what is the requirement here? The motor is to required to run at 600 rpm. Therefore at 600 rpm, now if you notice here, because it is mentioned field current is maintained constant by separate excitation mechanism. Therefore as the speed is reduced by half, back EMF will also reduce by half. Therefore back EMF will be 200 by 2. I can take this is a 100 volt. But what is mentioned that at 600 rpm the motor is required to operate with the regenerative braking. Therefore you have to find out terminal voltage by reversing this back EMF polarity due to regenerative braking. So you have to take 10 into 1 only. Why? Because it is required to maintain that armature current of the motor to be maintained at a rated value. So when you maintain armature at a rated value, there is no change in the armature current. So this value will be minus 100 plus 10. So this is equal to minus 90 volt. Now as this motor is controlling by of single phase fully controlled converter, this VT has to supplied by phase controlled rectifier circuit. If you simply look into the high level system diagram, it will be something like this. Therefore, what do you mean by this one? Here single phase full converter bridge is there. So this full converter bridge is supplying DC motor. Then what do you mean by this? Terminal voltage of this DC motor will be given to output voltage of the full converter will be given to terminal voltage of the DC motor. Therefore, VT of the converter should be equal to minus 90 volt. We know that, or try to recollect from rectifier chapter, what is VT formula? 2Vm by pi into cos alpha is equal to minus 90 volt. Therefore, cos alpha is equal to minus 90 into pi divided by 2 into Vm. Here Vm you have to substitute, you should be careful here. Vm you have to substitute source voltage of the bridge circuit, that is 240 volt is RMS value. Vm means RMS value multiplied with root 2. Okay. So from this, if you calculate, you will get firing angle alpha is equal to 114.6 degree. Okay. So this firing angle will be 114.6 degree, right? So this is the answer for the question. Now let us move to the next question. This is another question from GATE 2024 power electronics subject. A single phase half controlled bridge converter. So you can also say that the circuit is single phase semi converter. Single phase semi converter supplies an inductor load with ripple free load current. What is the triggering angle of the converter alpha is given 60 degree. The ratio of RMS value of fundamental component of the input current to RMS value of the total input current. Indirectly it is asking what is the distortion factor of the input current. So first let us find out what is the formula for RMS value of the fundamental input current. 2 root 2 by pi into 2 root 2 by pi into I naught, where I naught is the load current, multiplied with cos alpha by 2. So most of the students confused in this question, as the load current is not given, how to calculate. No need to worry about it. When you are taking the ratio, that I naught will get cancelled. So this will be 2 root 2 by pi I naught into cos, as alpha is 60 degree, cos alpha by 2 will be cos 30. So that you will have root 3 by 2. Therefore, this value will be root 6 by pi multiplied with I naught. Next, what is RMS value of source current? If you look into, or if you recollect, the source current waveform of single phase single phase semi converter will be quasi square waveform. Okay. So this is alpha and this is the pi, and this is I naught. Therefore, what is RMS value of this source current? Magnitude square multiplied with function duration, that is pi minus alpha, divided by half cycle. So that will give you pi. Therefore, it is equal to, so this is, this is I naught. This is I naught. Okay. So it will give you I naught multiplied with square root of pi minus alpha divided by pi. So I naught into square root of pi minus alpha is given pi by 3 divided by pi. So it is equal to I naught into square root of 2 by 3. Now as per the requirement, let us take ratio RMS value of fundamental input current, that is IS1 divided by IS. It will give you root 6 by pi into I naught divided by I naught multiplied with root of 2 by 3. So here I naught will cancel. Then you will be remaining with 3 by pi whose numerical value is 0.955. Okay, so for this question the answer will be 0.955. So these are all the different questions from power electronics chapter subject in the GATE 2024. By the way, I am Shankar, working as a faculty in Women Institute, Hyderabad. I passed out in power and control specialization from IIT Kanpur. If you are interested in any courses, GATE courses, or we are offering the coaching for GATE as well as assistant engineers exam and several PSUs in the electrical and electronics branch, of course EC branch as well. We have very talented pool of faculty. If you are interested, if you are looking for any further coachings, you can contact either this given number or you can go through the website given here. Thank you for watching.